So whatever we say is going to be immortalized on YouTube. Okay. I should warn you about that. And yes, you have his backup in case you miss, but still, please try not to miss. Okay. So once all the syllabi schedules are gone around the room, I'll talk about that. In the meantime, so I'm Jim Lambers. I'm a full professor in the math department. This is my 11th year at USM. Got my undergrad at a different black and gold school, bachelor's at a different black and gold school at Purdue, and my master's and PhD at Stanford. I've taught previously at Iowa State, University of California, Irvine, and Stanford. And the research specialty actually relates to differential equations. It's really numerical analysis, which is taught in at the undergrad level at Math 460 and 461, which a few math majors in this room possibly might take. But my specialty is in numerical methods for solving partial differential equations, whereas this is a class on ordinary differential equations. Okay. And it's my third time teaching this class here at USM. Okay. Almost everybody have? Okay, almost. Okay, I'll get those later. Okay. Thanks. Okay. Now, so what this class is all about is solving ordinary differential equations. Ordinary meaning where the solution depends on only one variable, x or t. We'll see some examples of that today. We're just going to tiptoe in. We'll see some differential equations, learn how to classify them, and then we'll go from there. Now, on the syllabus, it does not show my office hours. They had not been determined at the time that I made this document, but I can tell you them now. Okay. It's nice of whoever to provide working markers, a luxury we do not have in Southern Hall. Okay. And my office is in Southern Hall, near all the classrooms, Southern Hall 301. So, unfortunately, I do research with a lot of students, so I have meetings with them. It fills up a lot of my schedule, but there are holes in the schedule, and that's where my office hours go. So we have Monday, okay, 1 and 2 p.m. Let's see, Wednesday, okay, 12 and 2, Tuesday, Thursday, we have 9 a.m., 12 p.m., 5 p.m. And Friday, Friday's pretty blank for me, except for the 1 o'clock hour. And I'll add this disclaimer, or is it additional possibility? Not disclaimer, sorry. My brain's not working too well today, so just go with it. Or by appointment if none of these times work for you. While I do have a rather full schedule, there's often gaps come up, cancellations, things like that. There may be a way to fit you in. Okay. Now, next item from the syllabus. You'll see that there's a listing, there's a section on the course website. So definitely go there. So on the now you're going to have online homework. That's a separate thing, which I'll talk about in a bit. But the course website that's listed on the syllabus. So there's going to be pages there of particular interest. So the things I'm handing out are also there in case they need to be updated. A syllabus, schedule, and also I do have a full set of notes. That is posted on the resources page. There'll be a bunch of links down the left, syllabus, etc. And one of those will be the resources page. That's where you find a PDF that has notes, a full semester worth of notes. Now, and basically I'm going to be lecturing from that. So if you miss a day, you have a YouTube video. You also have the notes. Now, I should mention, since the last time I taught this class 3 years ago, the textbook has changed. So I am editing the notes as we go. I mean, pretty much everything is already there, but it has to be rearranged a little bit. So I would not recommend simply downloading them all at once, because they will be updated from time to time. So when you open them, on the cover page, there'll be the date, so you'll see when they've last been changed. Okay. But I recommend consulting that, because then all the details are there, but I'll also be following that pretty closely in class. Okay. One other thing, but I will point out to you, because as you can see on the schedule and in the syllabus, there are going to be 4 tests in total. So 3 during the semester, and followed by a comprehensive final exam. As we get close to each test, I will be posting practice tests that show you the type of problems that you can expect on a test, just with different particulars, and also solutions to the practice test to help you in study. Because I don't want a situation where I give a test and you come out of it thinking, I had no idea if I was going to be on the test. Well, yes, you're going to know what's going to be on the test. Okay, so and the first test is coming up, after Mardi Gras break. So a couple weeks before that, you'll see the first practice test. Before every test, the class periods before that is going to be set aside entirely for review, no new material. And that's when we can talk about the practice test or any other questions you have about the test. Okay. All right. Now, as far as the homework is, yes?
Oh, I'm sorry.
Oh, okay. Make sure it wasn't a question or anything. Okay. You have a big item from the syllabus. So the homework will be given through WebAssign. And what I've done is integrated the WebAssign course with Canvas. So what you should be able to do, and it looks like a few of you have been able to do that already, is if you go to this course in Canvas, on the front page, there's a link that will take you directly to WebAssign, so there should not be any additional, well, if it's your first time, I guess it'll have you create an account. But after that, it should just be go from WebAssign directly to Canvas without having to do any additional sign-in. The first 3 assignments for Chapter 1 are already up there. Now, has anyone, how many of you have actually gone to WebAssign? Okay, yeah, just a few. And if you do it through Canvas? Okay, so I want to make sure that's working. If you have any technical difficulties, so I urge all of you, go check that out today. Make sure you can at least view the assignments. If there's any problem there, let me know, because then if I can't fix it myself, then I can get on the horn to WebAssign and have them fix it. Now, as far as homeworks are concerned, all homework assignments will be due at 11:59 p.m. on Mondays and Thursdays. So, for example, if I finish covering a section on a Monday, since the class meets Monday, Wednesday, if I finish covering a section on a Monday, that assignment will be due the following Thursday. Whatever I finish covering on a Wednesday, like 1.1 today, that assignment will be due the following Monday. So the first assignment on the section I'm doing today, 1.1, you'll see that'll be due on Monday, January 27th. So not necessarily every Monday, Thursday. It just depends on how long it takes to cover certain sections. And of course, there's going to be a gap if there are tests. But I just want to get used to this rhythm right off the bat. That's when you can expect assignments to be due, so you can plan around that. As far as assignments are concerned, they can be turned in late to a certain point with a penalty involved, 25%. But all the homeworks together count for 15% of your overall grade. So each one assignment is going to be worth roughly maybe a little less than 1%. Lowest homework assignment gets dropped. Okay, and I forgot to mention it here in the syllabus, so I'll update it, but I'll announce it here today. Regarding tests, like I mentioned, 3 tests and a final. If you have from test 1, 2, and 3 to happen during a semester, if you have a bad test, or God forbid you miss a test entirely, there is still hope. So if you recover from a final. So what I'll do with a final exam grade is use that to replace your lowest from among test 1, 2, and 3. Unless the final is the lowest, so I'll only do that if it helps your grade. And the other thing I want to be clear about, because this is something, this department policy, so I have to follow that. No, you cannot get out of a final exam just because you got an A on test 1, 2, and 3. So everybody still takes the final, so don't even go there. That's something that has been done in the past, and department-wide, no, we can't do that. Okay, but if you've done that well in the 3 tests, chances are you'll do it well in the final anyway. Okay, are there any questions about the course? Anything that came up in the syllabus? Okay. So the schedule that you have here, unless there's something like a hurricane, well, this is not hurricane season, well, okay, tornado. That's what's more likely to happen at this time of year. So unless there's something disastrous like that, this is the schedule we're sticking with. So you know when each test is coming, what I'm going to cover on each day. When you go to WebAssign, you can see as I add assignments, like I said, only chapter 1 is there now. I'll be adding more as we go, starting next week, and you'll be able to see what's coming up due. All right.
When we get the book for the course, does it come with the WebAssign code?
It should. Those of you who got the book already?
I got the book. I didn't see a WebAssign code with it.
Okay, because if I go to... Does that happen to anyone else? Getting which edition was it?
I honestly didn't look at the edition.
That could be relevant. So in the syllabus,
Books,
it's the 11th edition. Is okay because also the I look up this course in the bookstore. It's also within WebAssign you have ebook access. So you don't even necessarily have to have a physical book. Okay. Okay. Math 285. Okay. Okay, yeah, so the bookstore lists only one format. So that's Do you have it with you? By any chance?
No.
Okay.
I left it back in my dorm.
All right. Check whether it's the correct edition. If it is, let me know.
Alright.
Okay.
It's the 11th edition, correct?
Yes, 11th edition. So did you get it at the bookstore or get it somewhere else? Or?
Bookstore.
Okay, then that should be right.
Alright.
Okay.
I probably just overlooked it.
Okay. Well, hopefully that's the case. All right. Other questions? Oh.
This is it?
Okay. Show me the others.
Yeah, this is the 11th.
Yes, that's the right book.
Yeah,
Okay.
a little thing on the back.
Yeah, that's it. I overlooked it. That's all.
Okay. All right.
It just happens.
Yeah. So there's the same one where it's not really a book, but it's just a bunch of pages put in a binder.
Yeah.
Yeah, that's what they sent me. It's like, no, I want something of a cover, which is also available. But yeah. Okay. Other questions? Anybody? Okay. All right. Now. So what I will do each day after class, when I get back to my office, I will start uploading the video from that class. So it should be up there like by that afternoon. And okay, on the course website. On the lectures page, that's the page that has the schedule. So with each lecture, on an entry in the table, that's where I'll post a direct link to the YouTube video. So first couple times, I'll send you all an email saying, okay, here's where you can find a video from today's class. And then after I should get used to it and just know to go there after that if you want to watch video, whether you were here or not. Because I know some. I do this for all my classes, and some like to go to the video even just to get some details they might have missed. Okay. All right. So we're going to tiptoe into differential equations in the next 50 minutes that we have here. Okay, caps don't stay in these markers, which is really annoying. Okay. All right. So, what is a differential equation? All right, so this is something that's quite simple to describe, anyway, is any equation involving derivatives of an unknown function. So you have some function that you're trying to find. That's your solution, and you're given an equation that involves derivatives of that unknown function. Okay. Now, there are many different ways of classifying differential equations. So I'll start with one of them right here. So an ODE, so an ordinary differential equation. So I will just refer to, I'm not going to keep saying differential equation all the time, we'll just call it DE for efficiency's sake. So an ODE is when the solution has only one independent variable. So it's a function of only one variable. So as an example, we could have, for instance, y prime of t is equal to 2t, for instance. So y is our unknown. That's what we're looking for. It depends only on t. Or another one, y double prime of x is equal to some constant that I'll call k times y of x. So here it's depending on only x. So throughout the semester, our solution will depend on x or t depending on the context. Okay. Now, by contrast, a partial differential equation, PDE, every solution depends on more than one variable. So an example of that would be partial derivative of u with respect to time, with respect to t, is equal to the second partial derivative of u with respect to x. So u is a function of x and t both. It depends on, so it's a function defined on space-time. Another way of writing it would be ut equals uxx. Okay. All right. Now, probably wouldn't be familiar with that notation unless you happen to take Math 280. Now, this course is only concerned with ordinary differential equations. So Math 285 is all about that. One undergrad course that we have that involves partial differential equations is Math 417 that's offered every spring. I know physics majors have to take that. Out of curiosity, I'm going to take a look at the roster and see what majors people have. How many math majors do we have here? Okay, not very many. Polymer science? Yeah. I knew Dr. Broadhead would send all of you here. So, what of our majors are represented? EET? Okay. Other ones?
Physics.
Physics? Okay.
Computer engineering.
All right. Okay. Cool. But yeah, when I look at a roster, it's like, wow, there's a lot of polymer people in here. So that's how the class got so big. Okay. Now, so from this point forward, we'll just forget about these and focus only on the ordinary case. Because the direction for this course is Math 168, so single variable calculus. Although, in a couple of places, partial derivatives do come up. So a little bit of Math 280, which I'll go over when the time comes. But really, partial differentiation is the same as call it ordinary differentiation. You're just focusing on one variable, taking derivative with respect to it. Okay. Now, other aspects that apply to any differential equation. Don't tell me this marker is giving out already. So classification of ODEs. Okay. So one aspect of an ODE that's very important is the order of an ODE. So what is that? That is the order of the highest derivative in the ODE. And so the course will break down to different orders of ODEs. So some examples of that. So like y prime is equal to 2y plus t. So there's only one derivative of this equation. It's a first derivative. So we call that a first order ODE. So the first major portion of the course, like chapter 2, is going to be all about exclusively first order DEs. Okay. Later, we'll get to higher order, beginning with second. Okay. So here's an example of a second order ODE that in time you will know how to solve. So we just look at what is the most differentiation has taken place, second derivative, so it's second order. Now, a point of notation want to deal with now, and then we'll see it again when we get to higher order equations. So I'm going to write down an ODE that is, say, 8th order. I know we're not really going to be dealing with that, although you will know how to handle it. I just don't think it's rather sadistic to give that as a problem on a test. But now I could do this. Something like that. That's a 8th order ODE. But who can tell me why it's a bad idea to write it that way? What's the problem with that?
Discount.
What?
Discount.
Yeah, it's hard to tell. I could tell you that's a 7th order equation, and you'd be like, oh, okay. Until you really get down and count 1, 2, 3. So we don't do that. So past order 3, let's say, we use a different notation. So this is the same equation. So we use the order of derivative in parentheses, very important, just so people won't confuse it with an exponent. Generally, I'll use like triple prime, but after that notation. You may have seen that, like taking Cal 3 and seen like Taylor's theorem is presented like that. Okay. So when you see an ODE, especially like in the final where it's comprehensive and seeing all different kinds, first thing you want to do is check what order is it, because you can have one set of techniques for first order equations and a whole other set of techniques for higher order ones. Okay. All right. Okay, so that's one key aspect of classification. Here's another. Okay. So differential equations can be either linear or nonlinear, and we're going to see mostly linear equations in this course, but we will encounter some nonlinear ones. Okay, so I will give more of an actual proper definition, but first some examples, and that might actually be easy for you to grasp. So here are some examples of linear ODEs. So this one is a first order, y prime plus 3t squared, y is equal to e to the t. And here's another that is second order. So y double prime plus sine t, y prime plus t, y is equal to 0. Now, so what we have here in these linear cases is each term. So by term, I mean all the things that are added together. So this differential equation has 3 terms on the left side. This one has 2 terms on the left side. So each term has to have this form. Is a function of t. That's what I have in these examples. Or it could be a function of x. Like I said, we're going to use x or t as the independent variable. Times some derivative of y. Now, when you have y by itself, you can also think of it as a derivative. It's the 0th order derivative. Just so everything's under one umbrella. So that's what we have here. Here we have y double prime times 1. Y prime times sine t. Y times t. Now, these functions, whatever functions you have multiplying a derivative, those do not have to be linear functions. Like this 3t squared here, nonlinear function of t, or sine t, also a nonlinear function. That's allowed. The differential equation is still linear. So when I say linearity, it's really linear in terms of y, not t, or whatever independent variable you're using. Okay. Now, to help you see it more clearly, let's show some nonlinear ODEs. So for example, y prime is equal to k times y. Now this by itself, what I've just written up to this point, is linear, but now I'm going to make it nonlinear. I'm going to put an exponent in front of a y. So it's y to the 1.1 power. Now we have a nonlinear function of y here. Here's another one, like y double prime is equal to e to the y. So when you start having nonlinear functions that depend on, that are nonlinear in y rather than t or x, that's when you get into differential equations that are nonlinear. Okay. I mentioned this one because that's an equation, seems a rather odd example, but I first saw it in a calculus book when I was teaching Cal 2. And what the problem focused on was showing that if you go ahead and solve this equation, this is an equation that you will know how to solve within a few weeks or so, that the solution blows up in finite time. It means you get to a certain value of t, and the solution becomes infinite, or there's a vertical asymptote. And for that reason, because the solution goes off to infinity after a certain amount of time, that equation is called the doomsday equation. But in that problem, while still called the doomsday equation, it was pointed out that y here, what does y represent? Population of rabbits. So at some point you have infinitely many rabbits. And that's doomsday. Okay, so like I said, we'll have mostly linear DEs like this, but occasionally we'll have something like this, some nonlinear take into account. All right. So that's another thing you want to look at when you're presented a problem with a DE, especially on a test. What order is it? And then once that's established, linear techniques that are specifically for linear DEs of first order and also higher order. If it doesn't follow, it helps you to narrow down your problem-solving approaches, because you're going to have this inventory of techniques in your head, and you're confronted with a DE, and you have to pick out, okay, which technique am I going to use? Which category does it fall into? And we'll have other classifications besides this, but this is a questions up to this point?
So,
Yes.
so it's effectively nonlinear is very similar to a linear in that it's each term is a function of t or x just multiplied by a nonlinear derivative of y.
There's more possibilities than that. For example, like, okay, linear, whatever function you have multiplying a derivative, can only depend on x or t. If whatever function is multiplying it also depends on y, okay, so actually I'll throw in another example, because yeah, this doesn't really cover, y prime is equal to, or y double prime is equal to y prime, for example. That's a nonlinear equation, because this derivative by itself of y prime could be part of a term of a linear equation, except it's multiplied by a function of y, not just x or t. I'll throw in one more. Y prime is equal to y double prime squared. So if you take any nonlinear function of a derivative, that's definitely going to be nonlinear. So first you check, does it fall into this description? So you include it's linear. Anything else is nonlinear. You have a question about that? One nice property of linear equations, especially this one, where it's equal to 0 on the right-hand side. In fact, I'll throw in these terms because they're going to come up later anyway. This equation is said to be homogeneous because everything's said equal to 0 on one side, and actually, really, the proper definition is y equals 0 works as a solution. If I set y equals 0 in here, this equation will be satisfied. Whereas that's not true here. If I plug in y equals 0, I'm going to get 0 on the left-hand side. Still going to have e to the t, which is never 0. So this equation is inhomogeneous. So we'll learn how to solve, when we get to higher order equations, we're going to cover homogeneous first, and then we're going to build on that to be able to solve inhomogeneous ones. But the reason I mentioned this here is that when you have a homogeneous linear equation, if you have any two solutions, their sum or difference is also a solution. Or if you multiply the solution by a constant, it's still a solution. So in other words, any linear combination of solutions to this is still a solution. That's something that's going to be very helpful to us when we try to describe, because often we're going to try to describe all possible solutions of a differential equation. The solution of a differential equation, especially these linear ones here, is not unique. There's always something that's undetermined. And it's literally a special case of this. It's something you're familiar with already. In Cal 2, whenever you had to take the integral of a function, what did you have to write on the end to get full credit? Plus C. And in Cal 2, there's probably something that was an annoyance. Excuse for your professor to take off points. But here that has actual meaning. We're actually going to make use of that. So solutions. So for any, especially linear differential equation, there will generally be infinitely many solutions, and then we have to specify additional conditions in the problem to narrow it down to a unique solution. That's something I'll talk more about on Monday. Okay. All right. So in fact, I'm going to expound on that now. That in Cal 2, you actually were solving simple differential equations. It just probably wasn't described that way. Okay. So if you were given this problem, you were tasked with computing the integral of some function f of x. I can rephrase the same problem as a dE. So you're solving y prime of x is equal to f of x. For that, all you would have to do is integrate both sides with respect to x. And once you integrate this side, by a fundamental theorem of calculus, the integral and derivative will, in a sense, cancel out, and you'll get y prime is equal to integral of f. And then what you'd have to do is work out that integral of f, if you can, and then go ahead and add on the plus c. Now, another...
So like integral and derivative cancel out, right?
Essentially, yes, that's what the fundamental theorem of calculus is saying. Yeah.
Should it be yx? Or am I just...
Whoops.
Yeah.
Yeah, I told you my brain wasn't working so well today.
Exact same thing.
You'll have to keep an eye on me. So. Especially today. Okay. Remember as at UC Irvine, I'd hear about cases where a student would do exactly what he did, like point out that there appears to be a mistake in the board. And the instructor in question would be like denying it. Like, wow. But yeah, it needs to be pointed out.
So how would that look as a double prime?
Actually, that gets to the next example I was about to do. Okay, so, and this is something that will appeal to a few of you in this room who are physics majors. Suppose we have a falling object. Now, we're just going to keep the situation very simple. So I'm going to let h of t, that will be our unknown. So this is going to be the height of the object at time t. And here we have what's called an initial condition. We're going to see a lot of this all semester long. H of 0 is going to be specified. So this is the initial height of the object, the height from which it is dropped. Okay. And I'm also going to impose, I'm going to impose a second condition, initial velocity. So, well, how would velocity relate to the height? How do velocity and height relate to one another? Calculus-wise. What?
Acceleration?
That'll come later. But someone said it? Yeah. So velocity is the derivative of the position or height in this case. So I'm going to specify that h prime of 0, which we can refer to as v of 0. So if I use v of t to refer to velocity, but that's also h prime of 0, that'll be some given constant v naught. So h naught's the initial height, v naught is the initial velocity specified in consistent units. Okay, conditions, but I need a differential equation that describes the height coming from physical laws. That's where a lot of differential equations are derived, and we'll see some examples of this as we go. So the actual ODE is h double prime. So second derivative refers to what?
Acceleration.
Yeah, second derivative is the yeah, okay.
I had a hiccup for a second. I was like,
Yep. Is the acceleration. So now if we're keeping it simple, we're not dealing with things like air resistance and so forth. We're just taking into account gravity. What should I put here?
Like 8 meters
Well, yeah, it'll be the constant for gravity. And since the object is, and we'll assume that going up is positive, so it's going to be minus g. So if I'm specifying the initial position, height for which it's dropped in feet, and then therefore velocity has to be feet per second, then g would be 32 feet per second squared. Okay. So now this is our ODE, and it's similar to this form here where we just have only a constant on the right-hand side. So in this case, we just go ahead and integrate both sides with respect to t. So if I have the integral of h double prime of t dt is equal to integral of minus g, that's a constant, dt. Okay, so derivative integral canceling out, but it's only going to cancel one of these derivatives. So at least in this case, it's correct for me to write the prime. So what's going to happen here when I integrate that? Yeah, so I get a minus gt, and we need a constant of integration. Okay. So we don't have a solution just yet, but we're on our way there. And the reason why, notice I had imposed two conditions on h. I had a condition on h of 0, I have a condition on h prime of 0. Why? Because the ODE is second order. So first part of this course, we deal with first order ODEs. We'll have one condition that we refer to as an initial condition. When we move up to second order, so whatever the order of the DE is, that's how many conditions you need to nail down a unique solution. Because right now, this is a velocity, so I can call this v of t. But it's not specified uniquely because this will satisfy the DE for any value of c. But now I need to take into account this condition right here. So in order to do that, I will set t equals 0 on both sides. So v of 0, which is the same as h prime of 0. So I plug in t equals 0 here, and all I get is c. But I look at my condition here, it also has to equal v naught. Therefore, c has to be, that is what satisfies at least the second condition. So we haven't specified the position yet. We're not done. But at least now we have the velocity. Questions about what's been done so far? Okay. So now, this being a second order ODE that we started with, bless you, we need to integrate one more time. So the integral of h prime of t dt will fill in what we have here. So we have minus gt plus v naught. Okay. So now we can integrate both sides again. So I have derivative integral canceling out on the left side, so we now have h of t. And what happens when we integrate that with respect to t? G is a constant.
G squared.
Minus g t squared, what's missing?
Over 2.
Over 2. Yeah, the integral of t is t squared over 2. And then v naught is also a constant, so we integrate that. And we get what? V naught times t. Okay, and yeah, we still need a plus. Actually, to distinguish from a c over there, I'm going to call this d. Okay, so solving second order ODE, you actually have what's called a two-parameter family of solutions, two constants of integration. It's just that at this point we've already determined what one of them is. Now we determine the other one. So now plug in t equals 0 on both sides. So we have h of 0, which by the condition over there has to equal the given value of h naught. If we plug in t equals 0 over here, and we get d. So d is equal to h naught. So now we are done. So the height at any time t is the familiar minus 1/2 dt squared plus v naught t plus h naught. So take into account only gravity. That will give you the height of the object at whatever time t.
So when you solve the first instance, you have your plus v naught, basically. Then your second instance gave you your h naught, correct?
Yes. Now, in this case, we had ODE that was simple enough that we could just go ahead and integrate both sides. Generally, you cannot. The kind of DEs we'll see in this class. So in some cases, you may have to rearrange first and then integrate, or there's other procedures that we'll learn. But we still see some concepts are going to apply across the board. For instance, I can say that the general solution which we'll see again and again this semester, of the DE that we started with, h double prime g, is the following. So h of t is equal to minus 1/2 gt squared plus ct plus d, where c and d can be any constants. No matter what their values are, this function will satisfy that. So that's what's called the general solution. Is a function that describes all possible solutions. To pick out a particular one, conditions. So the initial conditions, in this case, we specify the initial height and the initial velocity. Generally how you proceed, given a DE, in some cases you won't be given any initial conditions. You'll be given only the differential equation, and your job is to find the general solution that's going to be in terms of these arbitrary constants. So whatever the order of your DE is, that's how many constants you will have. So first order DE will only have one. In other cases, you'll be given what's called an initial value problem. You get a difference like the ones over there. And that's when you narrow it down to a specific function that satisfies all of that. Okay. Questions? All right. 15 minutes to go. Okay, so one other thing I need to discuss, this will come up on the first homework assignment, is once you solve a differential equation and any initial conditions that you're given, where's the solution actually defined? So we need to know the region of validity of a solution. Not an issue in this example, because we just have a quadratic function. A quadratic function is defined on the entire real number line. You can plug in any t. But there are some cases where the solution is only defined on a particular interval. Okay, so this leads to a term that is the interval of definition. The interval of definition of a solution of a nth order DE. so first order, second order, whatever we have, is, so what is that? It's an interval on which the solution itself and all derivatives of a solution up to order n they have to be defined, and it must be continuous. Right? Because if a function is not continuous at a point, it doesn't have a derivative there either. So it's not enough that the solution itself be defined on a certain interval. Its derivatives must be defined as well. And I have a couple examples. Okay. So first, this is the ODE I made up. 1 minus t squared y prime plus y is equal to 0. So this is a linear first order DE. And right now I won't get into the mechanics of how you solve it. That'll be one of the methods that we will see later on. Solving this one requires some real pain in the butt calculus, like techniques like partial fractions. But right, how does it behave? So for this example, I'll just, and I say a solution because, as I mentioned before, a solution is not unique. I'm just picking out one. So if I take this function, square root of t minus 1 over t plus 1, if I were to substitute that into, and you will have some homework problems that are about verifying that a given function is a solution of a differential equation. But that's just a calculus exercise. To verify a solution, you take whatever derivatives are required, plug it all in, see if the equation is satisfied. So for now, you can just take my word for it that this must satisfy this DE. But what we want to focus on here is where is it defined? Or it might be easier to ask, where is it not defined? Where is this? Sorry, what?
T equals 0.
That's true, it's not defined at t equals 0. What's the problem at t equals 0?
It becomes a negative.
Yeah, square root of a negative number. Okay, so that's one thing that could go wrong, is taking a square root of a negative number. What else could go wrong?
1 and t equals 1. And negative 1.
Yeah, t equals negative 1. What's the problem there?
You get to 0.
You're dividing by 0. Okay, so this is undefined at t equals minus 1, because we're dividing by 0. And if we have this situation where t minus 1 over t plus 1 is negative, we have that problem also. Okay. Now, let's look at a derivative. We take the derivative, and taking a derivative of this function would be a bit of a pain because it involves the chain rule and the quotient rule. But I'll just write down what it is. So it turns out to be 1 over t plus 1 squared, square root. And the square root actually flips. So this derivative, still undefined at t equals minus 1, but where else is it undefined now? Yeah, t equals 1. Now these issues, with the solution also issues for a derivative, but now we have something more, that t equals 1 is a no-no. So what can we say about intervals of definition? So to describe all the possibilities, let's draw a real number line here. Okay, so at -1 and 1, we know we have a problem. We have division by 0 either in the solution itself or over derivative. But what happens in between? It was also pointed out that t equals 0, we have a problem. We're taking the square root of a negative number. Now, so over here, we have t being greater than 1. So in that case, this portion is certainly going to be positive. Now, if t is greater than 1, then, so in other words, t minus 1 is positive. T plus 1 is also going to be positive. So here, the solution is defined, and the derivative also defined. So you confirm that you're taking a square root of a positive number in this case. Same thing over here, t less than 1. Also defined. You're not dividing by 0. And if you look at the solution and the derivative, if t is less than 1, that means that t minus 1 is negative. Minus 1. So t plus 1 is negative. If t plus 1 is negative, t minus 1 is also going to be negative. You're going to have a negative over a negative in both cases. In other words, you're still taking a square root of a positive number. So over here is defined. So, but what happens in between? Well, actually, will be continuous. So right here we have t minus 1 is positive, t plus 1 is positive, so everything's okay. Here we have t plus 1 is negative, t minus 1 is negative. What happens in between? Signs are different. Therefore, what? What? Undefined because? Square root of a negative number. All right, so here, in other words, if we want a real value solution, we're not going to get anything in here. If you're okay with a complex value solution, then okay. But we're concerned with real value solutions. So the intervals of definition are minus infinity to minus 1, so out here, and 1 to infinity. And notice I have the open intervals here. I have a parentheses, not a square bracket. So I have minus 1 and 1 excluded, those particular points. So anything strictly greater than 1, strictly less than minus 1 is okay. So these are things to watch for. Division by 0, square root of a negative number. Other possibilities, for example, taking a natural log of a number that's not positive, undefined. So things like that are what you watch for when determining the interval of definition. And I have 3 minutes left, which is just enough time for my other example. I have y times y prime is equal to t. We will learn how to solve this in the next chapter. But I can write down a solution. Y squared is equal to t squared plus 1. So notice I don't have y of t equals something. It's an equation. So y is implicit. Is implicitly defined by this equation. Because if I try to solve for y, I have to take into account positive and negative square root. And this is defined on the entire real number line, minus infinity to infinity. Because if I plug in anything for t, right side's going to be positive. So I have no problem taking the positive and negative square root of it. So for any t, there is a y. And if I were to, now that's for a solution. Y prime, if I were to take a derivative of both sides, like this is implicit differentiation like you learned about in Cal 1, I get the following. Y prime is equal to t over y. But because of this equation here, we have to make sure that y is never 0, and it's not because not only is the right side, so y equals 0 is not going to happen. So we're never going to have our derivative be undefined. Now you do have to check both. This is a first order DE. We check the solution implicitly or explicitly and the derivative, and that's how we can confirm that it's defined on the entire line. So be sure to check, like for second order DE, check the solution, first derivative, wherever all three are defined, that's the interval definition. Okay. So check WebAssign. Make sure you can get in. If you have any difficulties, let me know.